Hi, let's talk about our work on volume computation for SMT formulas. So you all know about this problem of Boolean satisfiability or SAT. So SMT extends this notion of satisfiability with something called theories. So in case of Boolean satisfiability, your variables are all Boolean. In SMT there are dozens of theories. The specific theory we are interested in is called the theory of linear real arithmetic. And in case of linear real arithmetic formulas, the variables are all real variables, and these constants that come from theory are the linear inequalities. Now these theory constants are connected by an arbitrary Boolean connector. So given this SMT formula, the problem we are interested in is to quantify the solution space of this formula. In case of LRA, as the variables are real variables, so the problem becomes a problem of volume computation of the solution space. Now if you look at the solution space of LRA formula, the solution space consists of this conjunction and disjunction of hyperplanes. Now the boundary of the solution space is linear because the constants are actually linear inequalities. But there can be non-convexity in the space because the Boolean circuit which connects these linear inequalities can have disjunctions. Now we know efficient algorithms for volume computation for convex polytopes, but those algorithms do not work for non-convex bodies. So in this work, we will design an efficient algorithm for volume computation for this problem. So our volume computation algorithm comes in 3 steps. So given the SMT formula, we decompose the solution space into convex polytopes which can potentially have overlaps. Now we discretize the solution space such that there is a relation between the number of lattice points in this discretized space and the volume of the actual polytopes. Now given this discrete space, we compute an approximation of the number of lattice points in the union of the space, and using this approximation we can compute an approximation of volume of the union of space as well. We can show that our algorithm comes with theoretical pack guarantees. Our algorithm works really well in practice. This can solve 8 times more instances than the existing tools could have solved. To conclude, we have solved an interesting problem which comes with theoretical guarantees and works really well in practice.